Good morning. Welcome to class. Glad you're here. It's a Monday, new week. Today, we're going to be continuing our discussion of exponential functions. And what we're going to do today specifically is focus on how we move from one part of our multiple representation web to another. Specifically, how do we move from a graph of an exponential relationship to its equation? So that's what we're going to look at today. Let's go to our book. So the title for 815 is What are the Connections? And specifically moving from a graph to equation. So in lesson 8.1.2, we started a multiple representation web for exponential functions. Today, we're going to focus on the development of a method for writing an equation from a graph. As you find ways to write equations based on graph, you'll build a deeper understanding of exponential functions. So as we proceed, keep asking yourself the following three questions. What information do we currently have? Can we use other representations to help us think about our equation? And how can we be sure that the equation we end up getting is the correct equation? So let's go ahead and start. And to start, we're going to begin with four graphs. And each one of these graphs contains clues to a specific exponential curve. We are told that for each of these, let me actually read this. It says, assume that if the graph has an asymptote, it is the x-axis. And that just has to do with the fact that, let's not get into it too much, but these curves can be shifted up or down. And I think that's something that you'll do in Math 3, perhaps a bit more. Right now, we're just keeping them so that if they have an asymptote, it's going to be right along the x-axis. So let's look at our first curve. So this first curve, in a way, it's a little deceptive because when I see that, I'm immediately thinking that there's a slope of 2, right, up 2 over 1, and a y-intercept of 5. And it would not be incredibly wrong if I said, well, you know, y equals what, 2x plus 5. The problem is what that would be, it would just be this line, right? Let me just grab this thin line. It would be this line. And we're not trying to find the equation of that line. We're trying to find the equation of this exponential curve. One of the things that I think often helps me when I'm doing this is to move from this one representation of the graph to a table. So I just find that it's easier for me personally to kind of offload the information from the graph into this table format to help me see what's going on better. And I do know that when x is 0, right, this curve is hitting the value of 5. The other thing that I know is that when x is equal to 1, it's hitting 2 above 5, right? When x is 1, it's 2 above 5, which is the number 7. Now, if I'm thinking about an exponential curve, the thing that I need to know is what is my multiplier, right? This is related to a geometric sequence, and when x increases by 1, the question is what do I multiply by to move from 5 to 7? Well, because these two values are adjacent to each other, I can take the newer value, 7, and divide it by the value that precedes it, 5. And I get here a multiplier. In fact, if I was to throw the calculator up on the screen, whoops, I think I did this already, yeah. If I take the number 5 and I multiply it by, open parentheses, 7 divided by 5, right? 5 times 7/5, I see that I get a value of 7. So multiplication by 7/5 does transform the number 5 into the number 7. So I have here my 0th term, 5, and I have my multiplier 7/5. So I think I can safely write the equation here, y is equal to 5 times 7/5 raised to the x power. The only other thing I might want to do in terms of answering the question, do I know that I really have this? I could plug in my two x's and see that I get the correct y's, and I do. But it also might be nice to go ahead and just jump over to Desmos and take a look at these and see if it behaves the way it's supposed to. So in Desmos, I'm just going to go ahead and type my solution here. Y is equal to 5 times 7/5. And I will raise that, whoops, not down here I will. I will raise that, let me close parentheses, raise that to the x power. So once I'm looking at this graph in Desmos, I can see certainly, right, certainly when x is 0, I am hitting the number 5. But I can also see right here, right, when I'm entering 1, you can see that I'm hitting 7. So that is most definitely hitting those two values. So I have here this exponential curve that is the x-axis is serving as an asymptote, and it's hitting the two values I know I'm supposed to hit. 0 should give me 5, and 1 should give me the number 7. All right, let's move to our next problem over here at B. In B, again, I can see that I have two x inputs that are adjacent to each other. So I think I'm going to use the same strategy. I'm going to move from this curve, and I want to look at a table of values, so x's and y's. When x is -1, I'm hitting a value of 120. And when x is 0, I'm hitting the number 40. So these are exactly next to each other, right? It's just increasing by 1. So I can go ahead and take the value 40, and I can divide it by the previous value to figure out what my multiplier is. And actually this reduces, right? 4 over 12 is 1/3. So this is equal to 1/3. So I have here my multiplier, right? 120 times 1/3 is 40. And I also have my 0th term in the form of when x is 0, y is 40. So I think I've safely got this curve as well, right? Y is equal to 40 times 1/3 raised to the x power. And certainly last week we did notice that when x is -1, right, we know that 1/3 to the -1 power is the reciprocal, right? It was nice that we talked about that last week. So 1/3 raised to the -1 power is exactly the reciprocal here, right? So when x is -1, I end up multiplying by 3, because when I have a negative exponent, right, that's equivalent to the base being a reciprocal, and then it becomes a positive exponent. So let's look at this in Desmos as well and see if it hits the two values it's supposed to. So let me clear that function and go ahead and type y is 120. Nope. My 0th term is 40. Y is equal to 40 times 1/3. I'm going to close that and raise it to the x power. So here's this curve. Let's see if it hits the values it's supposed to. I need to zoom out a lot because I'm going to need to be able to see 120. So I can see 120 in there, but I need to change the scale of my x-axis. So I'm going to, on Desmos, if you hold your cursor over this, if you hold it over the x-axis and press the shift key on your keyboard, you'll get this indicating that you can stretch out the x-axis. I'm going to stretch it out so I can see +1, and I can also see -1. So when x is 0, right? When x is 0, I'm hitting 40. You know what? There's a nice way you can see these values too. If I was to enter a small table, I'll just plot these points so I can see it more easily. When x is 0, right? I think I'm hitting 40, and I can see that that's on the curve. And also, I go down and over. Also, when x is -1, I don't know why I'm putting this lower, I can see that I'm hitting 120, right? And I can zoom in on those spots a lot, and I can click on those. It's like, yeah, that is definitely where it's hitting. Another way that I can see those is instead of doing this table of values, I can just come in here. I can graph this line. You know what? I think that's good. Let's move on. Let's go to part C. So in part C, we are asked to come up with the equation for this exponential function. Pretty boring, but it is an exponential function. And we're going to go ahead and write that curve, right? So my 0th term is clearly the number 18, so I can write y is equal to 18. But the thing about this is if I multiply 18 times 1 times 1 times 1 times 1 times 5 ones, I'm still at 18. So my multiplier here is just the number 1. So this is my quote-unquote exponential curve. When x is 0, I get 18. And when x is 5, I get 18. In fact, when x is anything, I get 18. So I'm confident this is correct because when I plug in 0 for x, I get 18. And when I plug in 5, I get 18. So let's move on to A, B, C, D. So question D kind of gives us a look at some things that we're going to look at down below in further questions. So this is the first time that we're going to kind of see this. So again, I think it's helpful to move from this representation, the graph, to a table so that we organize the information in the table a little bit better. One of the things I know is that when x is 0, I have a y value of 7. So x is 0, y is 7. I don't know anything about 1 or 2, but when x is 3, I know that I should be hitting the value of 56. So let's think about this. It's an exponential curve related to a geometric sequence, right? So we know that we have a common ratio. There's a value that I keep multiplying by again and again to get future values. And if I start at this number 7 and I multiply it once, right, I get to the first term. Let's just say that the value we're multiplying by is b because, well, that's in the form y equals ab to the x. That's the variable that we're using for that parameter. And if I multiply by b again, I'm going to get the second term. And if I multiply by b a third time, I'm going to get the third value, which is 56. So think about what we've just written down. We're saying that if we have 7 and we multiply it by 1, 2, 3 factors of b, we get the value 56. Okay, that's incredibly useful because this is like an equation that we could probably solve for b and we would know what our multiplier is. Now, if you're like me, you're probably guessing values at this point. And this particular problem, it's easy to guess the value, right? We're going to know that we're right. But I want you to focus on kind of how we're attacking this because sometimes it's going to be very difficult for us to guess what the multiplier is. But I can certainly say 7 times b to the third power is 56. Look at it. It's 7b. 7 times b times b times b is 56. How do I solve that? Well, I most definitely can divide both sides by 7, and that would give me that b to the third power is 8, right? 56 divided by 7 is 8. Use a calculator. 7 times 8 is 56. Use a calculator if you want to verify that. So one of the things that we can do to solve this, I need to get this base alone, and this is actually quite nice. If I take and I raise both sides of this equation to the same power, if I have equal things and I raise to the same power, to the power of 0 would be a problem. But if I raise to the same power, I'm going to get equal things. So what I'm saying is if I have b to the third and it equals 8, it is certainly valid for me to say, well, let's take both sides of this and raise it to the 1/3 power. Now you might be saying, Mr. Roberts, why did you pick 1/3? Well, because I know b to the third to the 1/3, right? b to the third to the 1/3 is b to the first, right? If I have a power raised to a power, I multiply to simplify this. So this becomes very simply b to the first, or b itself, is equal to 8 to the 1/3 power. Well, you've seen problems kind of show up in our book where it's like the cube root of 8, but I just want to show you on your calculator, you can definitely evaluate that expression. Let me bring the calculator up here. So if I have 8 and I want to raise it to the 1/3 power, I'm just going to go to the power of, and I'm just going to, up in the parentheses, depending on your calculator, you may want to use I'm up in the exponent, but you may want to use parentheses. So I'm 8 raised to a power of, I'm in the parentheses, I'm in the exponent, and I'm going to use parentheses. So I'm going to go 1 divided by 3, close parens. So this is 8 to the 1/3 power. And when I evaluate it, it gives me 2. So I know that my multiplier is the number 2. And I know some of you are saying, but Mr. Roberts, I could see that already because I was just playing with numbers and I landed on 2. And I get that. I get that. That's not a bad strategy. However, realize that sometimes your multiplier is not going to be as clean as the number 2. So I can say here, I think I safely know what this equation is. I believe it is y is equal to 7, because that's my 0th term. I believe that I'm multiplying by 2 a bunch of times and then raised to the x power. Now, I'm confident that that works for right now, because if I plug 0 in, 7 times 2 to the 0 does give me 7. And also 7 times 2 is 14. 7 times 2. 7 times 2 is 14. Times 2 is 28. Times 2 is 56. So 7, 2, 2, 2. Right? 7 times 2 times 2 times 2 does give me 56. So it hits the 2 values. And I don't know that seeing it necessarily is important, but I could look at it in Desmos as well. Y is equal to 7 times 2 to the x power. And let me just hit home real quick. Boop. Yep, there we go. So that looks a lot like what we're seeing in the book. 0 is hitting the value of 7. And if I compress the y-axis, and I get to where I can see 3, let me graph the line. X is 3. So where those two things meet, right, where those two values meet should be, yeah, it is. Where those two values meet, it's 53 and 56. So when x is 3, y is hitting the value of 56. You can see down here, y is different things, right? On this curve, y's are different values, right? Y's are, and above here, y's are larger than 56. But when you are right there at that point when x is 3, y is 56. So we're good to go with that. Errol and Sandy were working on writing an exponential equation in y equals ab to the x form using this graph. While trying to write the equation, Errol stated, I think a must be 10 because the y-intercept is at 0, 10. Do you agree? Absolutely. Absolutely, because when a is 0, I end up getting a times b to the 0 power. That's going to make my multiplier the number 1. So that's definitely the case. So I know we're pretty secure in the fact that a is going to be our 0th term. But we still don't know what b is, Errol noticed. His teammate Sandy said, I think that 10 times b to the 5th power has to be 0.0032. How did she get this? Well, I really like this thinking, because what we do know is it's like we're dealing with this equation, right? We're dealing with an equation in the form y equals a times b raised to the x power. And we know our multiplier is the number 10, right? And we also have a particular point. And for this point, we have both a y value, which is 0.0032. Oh, I didn't mean to write equals twice. We have a y value of 0.0032. And we do not know our multiplier, but we do know the x value there is 5. So when I write this down, right, you can see, that's kind of nice, because there's only one thing I don't know there. I don't know what b is. And we might say, well, finding b could be very, very difficult. But as we've just seen, it's not as difficult as we might think. So if I take 0.0032 and I divide that by the number 10, you know that's just going to throw an extra 0 in there. Oh, and my calculator threw it into scientific notation. That's really cool. So I'm just going to go ahead and write this as 0.00032. And if I look at this, the scientific notation version, it just put 3.2 times 10 to the negative fourth power, which is the same. It's the same. In fact, you don't have to change that. You could use that value in your calculator. How do we know these are the same? Well, if I was to write this in standard form, not scientific notation, I have to take and divide 3.2 by 10 4 times. And to do that, every single time I divide by 10, my decimal moves over 1. So if I think about the decimal being here at the 3.2, that's 1 of them, 2 of them, 3 of them, 4 of them. So when I multiply by 4, I do jump exactly to the same value. So these are equivalent values. Okay, but that is what? That is equal to b to the fifth power. So what did we say we could just do? Well, I can raise both sides of this to the 1/5 power. So I can go 0.00032, and over here I've got b to the fifth. I'm going to raise to the 1/5 power because that's going to give me what b is. I'm going to do the same thing over here. So now, now I'm just going to go ahead and take this value, right? And it's okay to just use that because they're equivalent. And I'm going to raise that to the, and I'm going to go ahead and open parens, 1 divided by 5 raised to the 1/5 power. And I get this number. If I want to, I can kick this into a fraction. It's 2/10, so it should be 1/5. So I can see that, so my multiplier here is 1/5. That's very interesting. So b is 1/5. Now, how do I know I'm right? Well, I think I'm right, but how do I know I'm right? Well, I'm going to check this, right? I'm going to check this against a couple known facts. So let's write our equation down. We think our equation is y is equal to it equals 10 because my zeroth term is 10. 10 times 1/5 raised to the x power. So I'm going to take a different approach for checking this. I'm just going to use my calculator. So on my calculator, I'm going to go ahead and enter the number 10. Got it? And I'm going to, if I don't multiply by 1/5 at all, it's going to stay exactly the same. But I'm also going to go ahead and say times, and I want to ask this thing to display this as a fraction. So I'm going to go ahead and bring up a fraction. It's alpha, there we go, alpha y equals, so there's my fraction template, press enter, and 1/5. So I've got the number 10, and I'm going to multiply by a fifth five times, right? Because then I should get at the 0.0032. There's 1, 2, 3, 4, 5. And then it occurs to me, why do I want that as a fraction? I need to know if I've got 0.0032. So I'm actually going to hit math, and I'm going to ask it to please display that as a decimal. I changed my mind, and it gives me that number. So now that I think about the fact that I have a decimal there, let's do that again differently. Let's go ahead and take the 10, and I'm just going to press enter, and I'm going to multiply by 1 divided by 5. Now the calculator is going to treat these as a decimal, so there's 1, 2, 3, 4, 5. So I'm very convinced this is correct because when I plug in 0 for x, it gave me 10. And when I multiplied that 10 times 1, 2, 3, 4, 5 1/5, I can see on my calculator that's equivalent to 0.0032. Let's move on to our next problem. Okay, so let's finish here, and I apologize for the size of this font. So it says use Errol and Sandy's method from the previous problem to write the equation of an exponential function with an asymptote at y equals 0. So that y equals 0 is the x-axis. So our asymptote is going to be the x-axis. And it has to pass through 2 points, 0, 5, and 4, 12, 80. 0, 5, and 4, 12, 80. So we can see this a little bit bigger. Let's go from this representation of 2 points. We've got our x values and our y values. We have 0 is supposed to hit the number 5. 1, 2, 3, 4 is supposed to hit the value 1,280. Again, from 5 to 4, I'm multiplying by 1, 2, 3. This time there's 4 jumps, so B, 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 B. In fact, if I look at this, my x value is 4, and 4 minus 0 is 4. So I can see that this is b to the 4th power just by looking at the difference between these two numbers. So maybe I don't have to draw these pictures all the time. I can just take the x value at 1280, 4, and subtract the x value when y is 5. 0, 4 minus 0 is 4. So my 0th term is 5, so I've got y equals 5 times b raised to some power x. Okay, all I did is I put my 0th term in, 5. The other thing that I know, though, is there's this other point. Oh, and now that I look at it, this is nice. If I know my y-intercept, right? If I know the 0th term, I just put that 5 into this equation. Okay. And then I use my other point. So if I use my other point, I've got 1280, and that's going to equal that 5 times b raised to the 4th power. So I just have to solve for b, and we've been down this road before. To solve for b here, I'm going to divide both sides by 180. Let me grab the calculator. No, I'm gonna divide both sides by 5. So I've got the 1280. I'm just making up random numbers at this point. I got 1280, 1,280, and I'm going to divide that by 5. When I do that, I get 256. So I have 256 is equal to b to the 4th power. So I'm going to raise each side of this equation to the 1/4 power. B to the 4th to the 1/4 power will give me b. And over here it's going to be 256 to the 1/4 power also. So let's take 256 and raise that to the 1 divided by 4 power. Depending on your calculator, I keep showing the use of parentheses. It's completely not necessary on the TI-84 Plus. It will evaluate. If I just did 1 divided by 4, it would know that. But I want you to make sure that you're not raising it to the 1st power and then dividing by 4. That to the power has to be really 1/4. When I do that, I get exactly the number 4. So I know that b, my multiplier, is 4. Okay, so my equation is y equals 5 times 4 to the x power. Let's write that again. So we know a couple things, right? We know that our 0th term is 5, and we're using that here and here. By solving this equation, we're able to identify what our multiplier is, right? We're multiplying by 4 repeatedly, because when I evaluate this, that gives me just b. In fact, maybe that's why I'm confused. I wrote this backwards. This side becomes b. On the other side, it becomes the number 4. So I know that b, my multiplier, is 4. And now that I know that I was using green for that, Mr. Roberts. Now that I know that my multiplier is 4, I can write the equation. It is y equals 5 times 4 raised to the x power. Now, if I go back to one of the original questions today at the beginning of the lesson was, how do I know that this is correct? Well, I know this is correct because if I enter that 5 times 4 to the, if I raise it to the 0 power, I can see it gives me 5. If I go grab that expression and I edit it so that instead of being 0, I put 4 there, I can see that from my table when I enter 4, right, it better give me 1280. Well, when I do 5 times 4 to the 4th, it does give me 1,280. So I have it. So that's it. It's been a long, what are we at, 29 minutes, 30 minutes today. So thanks for sticking with me till the very end. And I hope that you can think about this. How is it that we can write the equation of an exponential curve when we know what the 0th term is, and then we know some other point some other point later on, or maybe even before on the graph, right? How do we do that? Because it's kind of a good thing that happened here today. All right, I'll see you in class, and I'll see you tomorrow morning. This is Mr. Roberts. Have a great day.